Well, we're going to talk about acids and bases today and how they relate to future chemistry that you're going to do, and certainly biology. So acid-base chemistry is very important for a lot of reasons, and it's good to know how they're classified and how they behave. And so we'll go through the checklist later on, but right now what we should do is talk about how acid-base chemistry works. And if we start with water, really the whole idea is that acid-base chemistry is focused on how water behaves. And water actually dissociates by itself. So if you have a glass of water, a beaker of water, it actually dissociates, right? To break apart, unassociates, it dissociates. This is called dissociation. It dissociates, but it doesn't do that very much. In other words, for water to break apart, it doesn't do that very much on its own. And this guy here is called a proton. We should probably make sure we know what that is, right? If you have a hydrogen ion, or atom rather, right? It has one proton and it has 0 neutrons. And then there's the electron on the outside, okay? But if that electron disappears, you're left with H+, and there's no neutrons, so it's a proton, okay? So that's why we call it a proton. It's a hydrogen ion or a proton. It's the same thing, so I would get to know that. This guy here is the hydroxide, and you've seen that before, okay? But it's important to remember that water is better described as an H+ and a hydroxide rather than thinking, oh, there's two H's together. The two H's are not together, right? So remember this, water dissociates, breaks into two parts. Now we should probably talk more about this symbol here, right? That's an equilibrium arrow, a dynamic equilibrium, dynamic, to move, right, to go back and forth. So it's called dynamic because it does go back and forth, all right? Goes this way at the same rate as the reverse. Now, you could say 20 miles per hour, right? So the cars travel on the street 20 miles per hour that way, but at the same time, cars are going the other way, right? But this is important to remember too, that just because these rates are equal, right? Just because the forward and the reverse are equal, doesn't mean that both sides are the same. Here's what I mean. If I take this water up here again, let's draw this obnoxiously big, okay? And there is an equilibrium. It does, in fact, have a forward and backward rate that are equal. But what you get is wee little bits like that. You do, okay? So yes, there's an equilibrium, but look how small that is. This is actually much, much smaller in scale, to the order of 1/1,000,000th. Okay? That's what we're talking about. 1 out of 1,000,000 does this. And we have ways of showing you that. Okay. So that's the idea, though, is that it's still going back and forth at the same rate, but there's a whole lot of water, very little of that. If we talk about acids now, right, we have seen this before in biology and physical science, for example, but let's make sure that we have a good understanding of it, because we probably didn't talk about it quite enough here. So when we talk about strong acids, okay, there's a characteristic about strong acids that make them strong, and yeah, they're dangerous. We're going to talk about what that means later on. So here's a strong acid. Most common strong acid, HCl. Well, HCl breaks apart 100%. And that's why we call it a strong acid. Okay? Because when HCl dissociates in water, these two never come back together. And you have to remember why. That if you have a water molecule here, remember that this is a 2. I'm going to zone right in on that. Okay, this is a 2. It's a partial negative charge. That's what it means. This is a partial. It's not totally a positive 1, but it's close, so it's relatively speaking is positive. All right? And what happens is they surround this H, and the positive sides surround the chlorine or chloride, and they never get back together. Okay? Water is strong enough to surround those guys, and they never come back together. So that's one of the strong acids is HCl. Another strong acid is nitric acid. 100% breaks apart into that. You can leave the 1 or remove it. You can still put a -1, same thing. Okay, so that's nitric acid does that. Okay, this is less common, perchloric acid, but it does the same thing. And then one of the more unique strong acids, this is the only one that does this. It actually breaks apart twice with 100%. And the first time it does this, and I want you to guess what happens. Right? It does this the first time. But then this, that HSO4, it also breaks apart into this. Okay, so that's why sulfuric acid is unique. It does that. Okay, these are the 1, 2, 3, 4 main strong acids that you should know. However, sometimes we say there's 5, and sometimes we say there's 7. Here's why. Let's look at these guys here. The chlorine here. Okay, and we're going to, let's be creative here. It turns out that we could, in fact, substitute others, because if you look on the periodic table here, we have fluorine and chlorine and bromine and iodine, and we probably should call it iodine, right? Chlorine, bromine, iodine, but we don't. Anyway, we could substitute these two for the chlorines. Okay, we don't substitute this guy. There's a reason why. He is ornery, and he is an electron hog, and he does not play well with others. Okay, but you could take the HCl, and you could have HBr, or you could have HI. Those are strong. You could have HBrO4, and you could have HClO4. Okay, so those are also strong acids. So all of these listed up here, all of them, those are strong acids. They are to be memorized. So we go back. They are to be memorized. And generally the rule is, if you're not a strong acid, then you're a weak acid. So if somebody says, well, Benway, is this a weak acid? Well, if it's not in this list, then yeah, it's a weak acid. That's absolutely how we do it. If you're not a strong acid, then you must be weak. Okay. So now we can talk about weak acids. Now, it doesn't mean they're not dangerous. That's not true. Maybe some of them are. Certainly some of them are in candy, for example, like citric acid. Some of them are in your pop, like phosphoric acid, okay? But some of them are pretty dangerous, like hydrofluoric acid. Told you about that fluorine guy. He's nothing but trouble, all right? So what do you do with weak acids? The most common weak acid is this guy, HC2H3O2. It is known as acetic acid, and that's because it comes from the acetate ion. And this is worth talking about now, because it's what we call an organic acid, right? So what happens is we have this interesting situation where it's a little bit different. And okay, the structure here for this, let's draw it this way. For carbonic acid, or I'm sorry, acetic acid here, it's actually, I'm going to draw it in 3 colors. I want you to draw that. Okay? Now, what happens is this is the this is the acidic hydrogen. Okay? This guy here is acidic. Okay? So when we have a chemical reaction, that is the hydrogen that breaks off. And so I want you to see that when you look at this diagram here, right? This looks like it's the acidic hydrogen. Well, actually, no. He kind of is, but he should be over here. But we draw him in the front so that we know it's an acid. So a lot of what we do is we draw the H's in the front. That way we can easily see it's a hydrogen, or an acid rather. But actually, it's over here. Okay, so this is acidic or acetic acid. Okay, another example of a weak acid would be something like HF. I told you that guy's nothing but trouble. Okay, now he's weak, but only because of the way he breaks apart. Let's talk about that. Weak acids break apart like this, just like water. Water is actually a weak acid. That's where you've seen this before. Okay. So here's this, and that might only happen about 1%. Okay? Don't be fooled, though, that weak acids aren't totally safe. This actually is used to etch glass. Right? So we use this liquid. It looks like water, absolutely. But you put it on glass, and it actually carves out some of the glass. So you really have to be careful with that. It's weak, but it doesn't mean it's not dangerous. Okay, so there's HF. We could go back to the acetic acid, and this happens less than 10%. Okay, so that's why it's a weak acid, just because of this equilibrium arrow. So that's why we draw those. So now you know if you have a weak acid, you draw this. If you have a strong acid, you just draw a straight arrow. Okay, so those are examples of the weak acids. Now we can talk about bases and how they behave. So bases are basically they when we talk about strong bases, your professors will say things like they are the group 1 and group 2 hydroxides. You're going to say, I kind of missed that. What do you mean? Group 1 and group 2 hydroxides. And if you're not paying attention, you're going to miss that kind of thing. All right? So what do we mean by that? Let's take a look at the periodic table here, a small version. You may or may not wish to draw that, but what we're talking about is over here. Okay, these are group 1 and group 2. That's why you have to learn your groups, your periodic table. So those group 1 and group 2 hydroxides. What does that mean? Well, we have hydrogen here, then lithium, sodium, potassium, rubidium, cesium, and so on. And then over here, what do we have? Beryllium, I think. We don't really talk about that one. But that's magnesium and calcium and strontium. Okay? These here, when they form with hydroxides, those are what we call strong bases. Right? The most common is NaOH. It's used in drain cleaner, like Liquid Plumber or Drano. Yep. Also called caustic. Caustic means it's harmful. But now we know it's strong, right? You see that? It's strong because we use a single arrow. And so it breaks apart 100%. That same idea as the acids, breaks apart 100%. Okay? If we took another example, another very common base is potassium hydroxide. And this happens 100%. Okay? So they never go. that guy, and then the hydrogens here would be around that guy. All right, they get so surrounded that they can't come back together because water is interfering. That's called solvation, by the way. We've talked about that. Okay, solvation, to separate with water, or a solvent. Okay, so that's how strong bases are. However, we should probably also make sure we talk about this situation. Okay, calcium can support 2 hydroxides, but this is different because it's a solid. Okay, so we have some adjustments to make here, because it doesn't dissolve in water, not very easily. Okay, either does this guy. He's also a strong base, so you can actually touch it. Okay, because it doesn't dissolve in water. Okay, but it does act like a strong base. It does act like a strong base when it is in acids, for example. So these are strong bases. We'll talk more about that later on. All right. But now let's talk about weak bases. Now there's plenty of weak bases, but they're not common, and we don't really spend too much time in first year chem. Okay. Certainly we'll talk about it in other courses. The most common weak base is this guy, ammonium hydroxide, also known as ammonia, right? Okay, and sometimes you'll see it like this, NH3. It's a weak base, so it dissociates partially, right? That's why we have the equilibrium arrow. And this is why you had to learn ions, so you could make the distinction here that NH4 is the plus part, and then the hydroxide is the negative part. Okay, so that is a partial equilibrium, or an equilibrium rather, and it's a partial dissociation. So that's one example of a weak base. And just another one called the amines, right? Still has the ammonia idea with it. Is if we took a methyl group, that's what that is, and you saw that with acetic acid, and we could draw that. And so what happens? Well, it turns out that bases are in the business of taking protons. They add protons. So what we would get is CH3, NH3 plus, and OH minus. You say, whoa, where did that come from? Well, we have a lot more to learn, but let me show you here. We can't forget about water. Water actually is part of this. I want you to start drawing water like that. Right? Water is going to be that OH attached to a hydrogen. That's a better way to do it. Okay? And so what happens is this acid actually loses its H to the base. Bases actually accept hydrogens, and so we'll get more into that later, but we have this situation here. And because he gained a plus, or gained a hydrogen, he becomes a plus, and the remainder of the water is like that. All right? So that's some simple, basic concepts of acid-base chem. So let's go back through, make sure that we have it. Okay. First of all, acids and bases are centered around the idea of water breaking apart into H and OH minus. So it's not two hydrogens that are attached together, but rather this situation. So start thinking of water as an H plus and an OH minus. Okay, and then we talked about where protons are coming from. This concept of dynamic equilibrium means it goes back and forth, and where dynamic means to move. And so this is called your dynamic equilibrium arrow, or just equilibrium. Okay, and water is going to break apart, but very small parts. Even though this is the same rate going back and forth, you still have very small amounts on this side. Okay, the strong acids are to be memorized, and this is the most common, hydrochloric acid. We'll talk about how to name those later. They break apart 100% because water surrounds these, and then positive and negative can't come back together. And these are the other common ones. Anything in this group is considered a strong acid. The reason you need to know that is because if you memorize the strong acids, any other acid that you encounter is going to be considered a weak acid. Now, weak acid, the most common one is acetic, right? Arguably the most common. And it's actually like this, okay? So the written formula doesn't look like the structure here. When you write out the structure, it looks like that, okay? Turns out the acid part is actually here on the oxygen here, okay? This is the other common weak acid, but it doesn't mean he's not dangerous, and so they have dynamic equilibrium also. Bases are different. They are strong group hydroxides and metal hydroxides. So these, right, from the periodic table, group 1 and group 2, they break apart 100%, so that's why we know they're strong. And again, it's because water surrounds them, right? And that process, when water, which is a solvent, a dissolver, surrounds them, that's called solvation. And then we talked about these two examples where they are actually strong, but they don't break apart in water. So we have a little bit more to learn. Now, we also have this situation here, okay? And this idea is that weak bases dissociate also, but with equilibrium. And so there's two common examples. So acid-base chemistry is absolutely important, and you'll use it not only in this class or future chemistry, but also in biology.